All right, so here we're going to take a look at polar coordinates. They're amazing and fantastic and awesome and stuff. Okay, so polar coordinates are theta. R is a radius, theta is an angle. Basically, the idea is you go out a certain radius. Hold on, I wonder if I can write on this slide. I think I can. Maybe, no. Oh well. Basically, you're going to go out a certain distance. Yes, I can write on this slide. Out a certain distance r, and you go around like this. Okay, so this distance is r, and then this aroundiness is theta. Theta is always measured counterclockwise. And it's because you have a right hand, right? So if you think about what your right hand looks like, and you like put your fist on the table, and you like give yourself a thumbs up, so this is your thumb, and you're like, hi thumb, your fingers go like this. I can't draw. Those are your fingers. So your fingers go that way because they go counterclockwise. So we have a right-handed coordinate system. Right-handed coordinate system. Okay, that's why it's counterclockwise. In case you're wondering why it's counterclockwise, it's because they assume that everybody's right-handed because left-handed people, like Sinistra and like blah, 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 and whatever. So it's right-handed because people tend to be right-handed, that's why. And that's why it's counterclockwise. I always thought counterclockwise is stupid. Why wouldn't they make it match clocks? And they don't make it match clocks because they make it match your right hand. So out along the positive x-axis, right hand rule counterclockwise r, comma, theta. So yes. So basically the idea is we go out, we go shoop. So we could say we went out 2 and then we went around 60 degrees. All right. So that's pretty cool. So this here would be 2, 0. We went out 2. We didn't go anywhere. This dude here would be 1, 30. This dude here would be 2, something, 2, 60. Yeah. Oh yeah, because we just did that one. This dude up here would be, so like normally I want to say it's 0, 2, because in regular like XY coordinates it'd be nothing in the X direction and 2 up. But we're again thinking in polar, so we're going out, like 2 out and all the way around, so that's 2, 90. This dude, and pause the video at any point when you're like, hold on, you're going too fast. Remember, you are in full control of this video, so pause it and see if you can get these. 2, 135. So this one would be 1.5 out, and it goes all the way around, so that'd be 180. This one only goes 1 out and goes around to 210. This one goes 1.5 out and then around 270 degrees. And this one goes 1 out and then around 315 degrees. Okay? So you can kind of see how those goes. Yay! Okay, now we'll do it with radians. So we got this dude 2, 0. Sorry, goes out 2, goes nowhere, 0 radians. This dude goes out 1, 30 degrees. But we memorized a while ago that 30 degrees is pi over 6 radians. Yay! And then this dude goes out 2, goes around, so that should be pi over 3. Yay! Then this dude goes out 2, goes all the way around, should be pi over 2. Yay! Okay, so you can do these in degrees, you can do these in radians. Isn't this fabulous? I know, you're so excited. Okay, now a neat consequence of this is I can either say I go out and I go around 60, okay? But I can also say, well, I go out and I go super duper around 420 degrees. And you might be like, well, why does this matter? And so this becomes a thing whenever you're solving problems of like rotation. So the theta ends up not just representing the local position, but it's kind of like a history of where you are and how many times you've gone around the circle. That sounds like very, I don't know, like hippy dippy. But like if you're doing some kind of like, if you're describing a particle and the particle is spinning around, if the theta is 60, you know that the particle is spun around it once. If the theta is 420, you know it's spun around it twice. But it's the same location, but it still gives you more information. Does that kind of make sense? So this is kind of a cool little thing that you can do with polar coordinates where it gives you actually more information about the behavior of the particle. So from a just kind of standard, we're just learning this in the classroom perspective with no context, 2, 60 and 2 comma 420. Again, just to make sure you got that, it's because you've got the whole idea of 60 plus 360 degrees is 420 degrees, right? That's where we got that, because it goes all the way around. They're just equivalent, because if you graph them, they're the same point. Philosophically, I guess you could say they mean something slightly different, but I digress. Okay, another thing you could do is you could go to the right and you could go around backwards. And that's kind of cool also. So you're actually going around negative 300 degrees. And this tells you that the particle is rotating clockwise. So a negative angle means that you've actually gone around clockwise, and this is giving you information about the particle. So technically, it's in the same location as 2 comma 60 or 2 comma 420, but it's giving you a little bit of an insight into what this like silly little particle is doing. Okay, so this dude, we can also have a negative radius. And a negative radius just means you go the opposite direction of the radius you're supposed to go, which is in the negative x direction. So I can also go negative radius all the way around negative 240. So again, this is just giving you information about what's going on with the system. So it's a little silly, but just to let you know, these all mean the same thing because they all end up going into the same location. We could also do negative 2 and then clockwise. So this would be a negative radius and a negative theta. So negative 2, negative 120, which is pretty cool. Okay, so for a problem like this, we would be looking for you to find different representations for all these points. So if we're looking for something with like a negative r, doing something with a negative theta, or doing something with a theta that's actually greater than 2 pi. So pause the video, see how far you can get putting these together. Okay, so let's start with the one that we already know how to do, which is this 260, and just make sure that we can do this. So we're going to do one with a negative r value. So that means we're going to go out negative 2, positive rotation, because it didn't specify, so we'll just stick with positive rotation, so that's counterclockwise. So we're going to go all the way around, like that. Got it? Make you happy? Okay. Yeah, okay, I like it. I like it. I'm down. Okay, so this is 180 degrees, and then I'm going another 60 degrees. So that's 240 degrees. So I'm going negative 2, 240 degrees. Yes, okay. Negative 2, 240 degrees. Beautiful. Okay. Let's see. Another way we could do it is one with a negative theta. So we're going to go out, and we're going clockwise, and clocks go this way. So clocky, 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 clocky. Okay. So that's 270 degrees, and then there's an extra 30 here, so that's 300. So 2 comma 300 degrees. I'm amazing because I can add numbers, and I swear it's not the 14th time I've recorded this particular point. Yeah. All right, and now we're going to do one with 2 pi. So this is indicating we want it in radians because it says 2 pi. So we're going to go out 2, and we're going to go, again, counterclockwise because we want it to be positive. So I was about to draw clockwise because I'm not paying attention. Hence the having to do the same point like 7,200 trillion times. So we're going to go doop, 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 all the way around once, and then we're going to go around up here again. Okay, so we went up 2 pi, and then we went around, so we went around 2 pi, and then we went up an additional pi over 3. So 2 pi plus pi over 3 is going to give us, times 3 is 3. 1 times 3 is 3. 2 times 3 is 6. 6 plus 1 is 7. Okay, 7 pi over 3. So we've got 2 comma 7 pi over 3. So if you're like, okay, I get this, now pause the video and see if you can do the remaining ones. I'm going to do them in like stoopy-doop order, like counterclockwise, positive rotation order. So see how far you can get. Okay, so let's go ahead and look at, we'll call this one B.
Okay, so again, in theory, you have paused the video and tried to do these. So we've got a negative r. So our negative r would be the negative 2, and then we're going to go ahead and go counterclockwise. So go all the way around, doop-de-doop-de-doop-de-doop-de-doo. This is 270, and then we're going to go another 45. So that's 315 degrees. 315 degrees. Okay. So I got that. I think. All right. And then I'm going to do a positive r, but this time, come here, r. Where did you go? Why are you not listening to me? There we go. Positive r, positive r, but now I'm going to do a negative theta. So negative theta, remember, means I'm like totally questioning myself now. Clockwise. So left-handed. Beautiful. Okay. So clockwise, that's going to give me 180 plus 45, and that's giving me 225. 225? Okay. So 2, 225. Beautiful. Excited. Feel like I'm terrified that I'm doing something. Is that the direction clocks go? Hold on. This is the direction clocks go, right? Yes. Okay. See, you get in your head and then your brain stops working and then you start freaking out for no reason, because brains are dumb. Brains are dumb. Okay. I'm just going to keep doing stuff and hope that I'm not doing something dumb. Okay, now we're going to do the exact same thing again, but now we're just going to do it with theta. So we're now going to do clockwise, because it needs to be counterclockwise. I forget which direction clocks goes. I just know the right-hand rule now, so clocks are stupid. And who has real clocks anyway? That's not true. I have a cuckoo clock in my in my house, and somebody was over at my house, and they're like, I didn't know those were real. And I was like, they are. Real people have cuckoo clocks. Or maybe they don't. Okay, so this is 2 pi. And then this is another pi over 2. And this is another pi over 4. Just in case you don't have these memorized, I'm just going to kind of do them like that. So I have 2 pi plus pi. Oops, math is math. Plus pi over 2 plus pi over 4. So really that's 2 pi over 4 and 8 pi over 4. So that's going to be, it was 8 plus 2 is 11 pi over 4. Yay, 11 pi over 4. So it's still 11 pi over 4. Gorgeous. Love it. Make you happy? Okay. Because it's important to be happy in math, you know. Okay. Love it. Okay. Next one. All right, so let's do this one. Let's do this dude. Okay, negative r, and we're gonna do this. Oh, to just go straight there. Look at that one. That one's so cute. -1, 30 degrees. Achoo. Just straight up 30 degrees. All right. What else can we do to get there? We can do a positive r. And then a negative theta. So I'm going to stop thinking clockwise, counterclockwise. I'm just going to keep using my hands, and this is the one that makes my thumb go into the page. So that's another way to think about it. Thumb, if you can keep your right hand, and you know which way is on your right hand. This is thumb into page. That's how your fingers curl, thumb into page curling. So it goes choo-choo-choo-choo, choo-choo-choo-choo. So that's 90 degrees plus 60 degrees. So that's 150. So that's 2, not 2, specifically not 2. 1, comma, negative 150. Beautiful. Love it. Love it. Okay. And then finally, we want to do a 2 pi thingy. So we're going to go out here and we're going to go aroundy, roundy, round. So that's 2 pi. And then we're going to go all the way here. So that was 2 pi plus another pi plus another, this part here is pi over 6. Again, just in case you don't have these memorized, 2 pi plus pi over 6, so over 12 pi over 6, maybe, right? 6 pi over 6, there we go. I knew I could do this, because 3 times, it's 18, it's going to be 19, right? Yes, okay. Like, I can do this in my head, I just can't do it when I show my work. So I have 1 comma 19 pi over 6. Oh, that was amazing. We get to do this 2 more times. Woohoo! Doop 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 doop. All right, let's do this dude down here. Okay, negative r. And if you're getting bored, that's good because it means you're understanding it. And if you're bored and you're not understanding it, then something else is going on. Negative r, and we're going to do positive rotation this direction. So it's negative 1.5, 90 degrees. Beautiful. Then we're going to do positive 1.5, but negative rotation. Right? Negative. Yeah, okay. Negative rotation. 1.5, negative 90 degrees. It's bothering me. Bothering me that those are just like flippy, the angles, but I think it's okay that the negative signs are just flipped. I don't think that's like, that's never happened elsewhere. I'm just going to stop, and I'm just going to have to trust that the math is doing what the math is supposed to do. That's clearly 1.5, that's clearly negative 90, and I need to get out of my own way when I'm getting right answers. Okay, and then someone's going to mention, like, clearly that answer's wrong. Shut up, your face is wrong. Okay, so now I'm going to do 2 pi, so I go all the way around, 2 pi, and then I got to go again. Here, and then all the way down to here. So it's going to be 2 pi plus 3 pi over 2. So 4 pi over 2, 7 pi over 2. So 1.5, 7 pi over 2. Yay! Okay, so you got that one. Chirpy, 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 chirpy. Okay. And then let's do this last one. So here, I guess we could have started with that one. That would have made the most sense. All right, so let's go here. So, oh wait, but we're doing negative r. So we're going negative r all the way over here for no reason. And then, whee! So that's 180 degrees. Negative 2, 180 degrees. Got it? All right. Then we're going to go positive 2 and negative angles. So we got to go all the way around. So that's positive 2, negative 360 degrees. Got it? And then we're going to do positive 2, and we're going to do this in pi. So we're going to go all the way around once. And we have to go greater than or equal to 2 pi, so we can just stick with 2 pi. So 2 pi. Hot dog. So we got that working. Okay, so let's start with the one that we already know how to do, which is this 260, and just make sure that we can do this. So we're going to do one with a negative r value. So that means we're going to go out negative 2, positive rotation, because it didn't specify, so we'll just stick with positive rotation, so that's counterclockwise. So we're going to go all the way around, like that. Got it? Make you happy? Okay. Yeah, okay, I like it. I like it. I'm down. Okay, so this is 180 degrees, and then I'm going another 60 degrees. So that's 240 degrees. So I'm going negative 2, 240 degrees. Yes, okay. Negative 2, 240 degrees. Beautiful. Okay. Let's see. Another way we can do it is one with a negative theta. So we're going to go out, and we're going clockwise, and clocks go this way. So clocky, 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 clocky. Okay. So that's 270 degrees, and then there's an extra 30 here, so that's 300. So 2, 300 degrees. I'm amazing because I can add numbers, and I swear it's not the 14th time I've recorded this particular point. Because yeah. All right, and now we're going to do one with 2 pi. So this is indicating we want it in radians because it says 2 pi. So we're going to go out 2, and we're going to go, again, counterclockwise because we want it to be positive. So I was about to draw clockwise because I'm not paying attention. Hence the having to do the same point like 7,200 trillion times. So we're going to go doop to doop to doop to doop all the way around once, and then we're going to go around up here again. Okay, so we went up 2 pi, and then we went around 2 pi, and then we went up an additional pi over 3. So 2 pi plus pi over 3 is going to give us, times 3 is 3. 1 times 3 is 3. 2 times 3 is 6. 6 plus 1 is 7. Okay, 7 pi over 3. So we've got 2, 7 pi over 3. So if you're like, okay, I get this, now pause the video and see if you can do the remaining ones. I'm going to do them in like stoopy-doop order, like counterclockwise, positive rotation order. So see how far you can get.
So now like a super important skill is being able to convert polar coordinates to Cartesian coordinates. And you're like, what's a Cartesian coordinate? So it's like, remember that like guy named Descartes or something? You maybe heard Descartes? Well, that's Cartesian. Cartesian just means the XY, rectangular coordinates, little XY thingies. So if you have something's in polar, can you convert it to XY thingies? Yes. Okay. So like if I have 2, 60, we'll go back to our old treasured 2, 60. If you go over here, you got choo-choo-choops, and you want to think about it. Come here, clicky, clicky, clicky. There you go. So you can kind of envision that you got yourself a triangle with its one little angle there at the origin of the coordinate system. And then you can kind of make the coordinate system disappear. So you got your little 60-degree angle down there. So think about that again. So you got that. So it went out 2 and around 60. So that thingy down there is the 60 degrees, and the 2 is going to be the hypotenuse. And so that's what you've got. You've got a right-handed, or sorry, not a right-handed. You've got a right triangle that has what do you call it? An angle that's 60 and a hypotenuse of 2. And now you have to figure out what the XY coordinates are that go along with that.
All right, so let's see what we can do with this. Okay, so I put this all back together. So we've got the 60. This is a 30, 60, 90 triangle. So in theory, you should be able to do this pretty quickly. This is the 2. So the opposite, the side of, sorry, not the opposite side of the 2, that's the hypotenuse. So that means the short side, since this is the 30, the short side is the 1, and the in-betweeny size is the square root of 3. So actually we're already done. You go out 1 and you go up square root of 3. So the XY coordinate for this is exactly 1, square root of 3. If you're like, but I don't believe in square roots or something, I don't know, you know what I mean? If you're like, I want a real answer, you can get a real answer. Square root of 3 is something 1.73. So you could say, well, it's technically 1 point something. I mean, technically it's not. Technically it's square root of 3, but regardless, you know, that's pretty straightforward, okay? So let's do it this way. So a lot of times you're just given just straight up the problem without the graph, and you kind of got to put the graph together. So we kind of draw ourselves a little polar plot here. We're like, okay, so it's 1, 2 out, and 135. So 135 minus 90 is 45. Okay, so it's going to go around 90, and then it's going to go around another 45. Okay, so there's my 45. So there's the 45, and there's the 2. Okay, so I'm going to draw that prettier. So I've got Pashoo, Pashoo, Pashoo. I said prettier, and I did not achieve prettier. So pachonk, pachonk, pachonk. That's infinitely prettier, right? So this is 45 degrees down here, and this length is 2 because it went out 2 and then around 135. Okay, so this is a 2, a 45, 45 triangle. So I know the 2 sides are 1, 1 square root of 2, right? So we did that on a different video where I had 1, 1 square root of 2. So if this is 2, to get to that, then that would be 2 divided by the square root of 2, which is just square root of 2. So basically that means the two sides are square root of 2. Okay? If you don't like the idea of doing it, I mean, obviously one day you can be given a problem that isn't a perfect, or isn't a perfect, but isn't a special triangle, and you can use trig, but we're just trying to get like the basics without you getting lost in the math. So if you're cool with the idea that it's 2 square root of 2 square root of 2, I'm going to draw this a little bit better now. So remember, this point was right over here. Okay? So the point is square root of 2 over, and I'm going to make these two different. It's this square root of 2 over, and then it's, we'll do this one, this square root of 2 up. I mean, technically we had it up on that side, but it doesn't matter. It's fine, because it's just a square. So we have square root of 2, square root of 2. So now we just have to be careful whenever we're actually making our xy coordinate, because our x coordinate is actually negative. So our xy in this case is negative square root of 2, because it goes back along the x-axis, and then it goes up the y-axis. So again, if you want to have yourself a pretty little fake answer that's a decimal, I knew that. I don't know why I did that. You could say it's negative 1.41, comma 1.41. Okay, so this also gives us an excuse to start playing with trig some more, but this is a good exercise in doing this.
Similarly, we would want to be able to convert these Cartesian or these rectangular coordinates to polar. So pretend we just had this y coordinate called 2, 2. So 2 out, 2 up. And we're like, okay, so if I think about it on this polar little graph thing, I kind of superimpose a polar graph. I think it's going to go out a certain roundedness, or a certain distance, and then go around. So out and then around. So whenever I think about going out and around, I think about what would that triangle look like. Okay, so if you go out and around, you'll have a triangle where you essentially have the two sides that are going to be 2 and 2, and then you have to figure out what the radius and the theta are from there.
Okay, so we can go ahead and we can label our triangles. Our triangle sides are 2 and 2, so this, doesn't look unfamiliar. So again, if we think about our 1, 1 square root of 2, 1, 1 square root of 2, then that means that our ratios are 2, 2, and then 2 square root of 2. So our triangle has a 2 square root of 2, and it's a 45 because it's a isosceles triangle. So this is actually almost faster. We can say that we go our r comma theta as it goes out 2 square root of 2. Oops. It goes out 2 square root of 2 and goes around 45 degrees. And again, if you want that to be pretty, 2 square root of 2 is 2.83, 2.83, and goes around 45 degrees. And the 2.83 makes sense because if you think about where these are, this is at 1, this is at 2, this would be at 3, so it's kind of almost at 3, and then it goes out and around. Cool. All right, one more. So now we're converting this Cartesian point to polar. So I'm just going to draw it out here. Dun 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 dun. So it's over here. All right, so it would have gone like all the way around. Okay, so I'm going to think about what that triangle looks like. I'm actually going to zoom in on this triangle. So I've got a triangle here. Triangle, triangle. And this triangle has a 4 over here, and it's 3 down, so it's got a 3 over here. So I'm going to redraw my triangle. 4, 3. It's a 3, 4, 5. That does not mean it's a 30-degree triangle. So just remember, this is a different theta. I'm not even going to call it theta. Let's call it phi, just so we don't freak out about it. I need to know what that angle is. It's this angle right here. I'm just drawing it off to the side in case you're having a hard time seeing it. So I can do my trig. I know that the tangent of phi is opposite over adjacent. So I know that phi is the arctangent of, what it was, opposite was 3, adjacent was 4. So arctangent, look, I knew I'd have to do this eventually, of 3 divided by 4, 36.9. Yeah, 36.9-ish? Yeah, okay. So theta equals, or phi equals 36.9. Now, that's not the theta I'm actually looking for, right? Because in real life, I had to go all the way around. It started here, and it went all the way around. So it actually went, so it went 180 plus that little bit. So I need to add 180 to that. So I end up with 217. So actually, I forget how they spell it on Reddit. I just know how to spell it correctly. The R theta for this is it goes out 5 and it goes around, I already forgot what the number was, 217. So 217. So hopefully that gives you enough to kind of get a basic idea of what we're doing. And it's really hard when you're doing these to get context of like, why am I doing this? This is stupid. And all things are stupid until all of a sudden you need it and you're like, oh, that was actually important. Like apparently knowing how to do laundry and cook is important, but I still think it's kind of stupid until somebody cooks for me and they cook well. I'm like, oh, that was actually kind of good. So anyway, along those lines, I can't cook, but I can convert Cartesian to polar like nobody's business most of the time. So that'll be fun. Enjoy. Go do math. Yay!